speak on Khovanov homology for thickened surfaces. It's written over surfaces, but yeah.
Okay, yeah, I think I read this. Yeah, I had written off surfaces, but I realized that it's not Khovanov homology off surfaces, it's for stuff within thickened surfaces.
Okay.
So I see my PhD advisor has to make sure that I write the things correctly. Thanks very much for the introduction and for the invitation. I'm really happy to be here. And so yeah, it's a great pleasure to be in such a place. I wanted to tell you about ways to extend Khovanov homology for surfaces. It's a somewhat old topic, but I'm hoping to revisit old construction a little bit and tell you about some new ones. So the general idea, and it's all a joint, so it's a mixture of joint works with Paul Wedrich and David Rose, meaning there is not one paper with the 3 names on it, but there are several papers with 2 names each time. Right, so the general idea is that Khovanov homology that's something for K in, say, S3 or R2 cross an interval. And the Euler characteristic of it is something that, so maybe this is the easiest way to write it here, since we've heard a lot about the Kaufmann bracket scale module, to say that the Euler characteristic of Khovanov homology is the Kaufmann bracket scale module of the knot. So that's related to the Jones polynomial. And one of the big features for the Jones polynomial is that it can be extended to an invariant of 3 manifolds. And so that's, for example, either Wittgenstein into Rayev or again Kaufmann bracket scale module. And so the question is, can we do the same for Khovanov homology? There are a few answers. So the first one is that's been done for thickened surfaces, which is the case I'm going to talk about. And it's due to Asaeda, Pshititsky, and Sikora. And in the particular case of the annulus, there also is work by Roberts. So that's been known for more than 10 years now. The other known cases are S2 plus S1, and that's due to Rosensky. So Y or I? Y. And the last one, the last one I know of is you can actually take several copies, connected sum of S2 plus S1, and that's due to Michael Willis a few months ago. And as far as I know, these are the only cases beyond S3 where we can just even define something. So I'm going to ignore these 2 completely and only talk about the first one. And so the goal of my talk is to try to recast this construction of Asaeda, Pshititsky, and Sikora in a more algebraic and maybe a little bit more conceptual way, so that it's a natural thing to do, and also so I'm going to refine the definition so that it has a little bit more features. And right, so it's based on work with Paul and David, and it also extends work by Grigsby, Licata, and Wehrli. So I'll first tell you a little bit more about Khovanov homology. I think Anna basically did all of the work, so I briefly recall a few things that I'll be using. So Khovanov homology is some process that starts with a knot diagram. So I'll take the first non-trivial link. I wanted to do it for the trefoil, but couldn't fit off the board. So I'll do it for the hop link. And computing Khovanov homology for it. Starts with computing the associated Khovanov's cube. So we resolve each of the crossing in all possible ways. That gets organized into some hypercube of resolutions. Like that, and something like that. And we have differentials in between that are defined so over the changing locus. So here I've changed the top crossing. I get a cobordism that I think there is no way you can see anything. I'll try to draw it a little bigger. So we locally have a saddle cobordism. And elsewhere, it's all just the identity cobordism. Okay, there are sign placements so that it's actually a complex, but let's not talk too much about that. And there's a grading I also won't be telling much about. All right, so that yields some complex in some category, and the category we're living in at that point is a category defined by Troll a few years ago. So I denote Bn, the category whose objects are closed curves on R2. So basically a bunch of circles on R2. Planar curves. And morphisms are cobordisms modulations that Anna already listed. Cobordism mod relations. And the relations are very easy to list. A sphere is 0. So formally they are, it's more like I'm allowing for direct sum. So here we have direct sum of planar curves. And here we have K linear for a choice of some fields, or Z linear combinations of so we have matrices of Z linear combinations of cobordisms. So all of this to say that there will be plus signs and multiplication by integers. Right, a dotted sphere, that's 1, and a dot is just a shorthand to say that I'm allowed to invert 2, and then it's a shorthand for a handle. If we have 2 high genius, then we just kill everything. And the last one, maybe the most important one, is a neck-cutting relation that tells us that whenever we see a cylinder that can be cut into composition of cap and cup with some dot placement. Okay, so the big theorem due to Khovanov and Van Natten for this precise version is that well, Khovanov homology, so I should say the bracket, the double bracket of K I defined over there, that so is not invariant or link invariant. Once I look at it as in the category of complexes up to homotopy over the Barnafian category, that categorifies the Jones polynomial. So this statement gives us tells us several things. First thing is that why do I go there? Clearly, if we just take the complex itself, that's not an invariant. If we change the diagram, we get different complexes, and they are not the same. They are not equivalent in the category. What Khovanov did was actually replacing the complex by a complex of vector spaces, and then he took homology and proves that the homologies are indeed isomorphic there. So that gives the so which I would like to do here is take homology of the complex. The issue is that the Barnardian category is not abelian, so we cannot define kernels and images, and so we cannot define homology. So we just mod out by homotopy equivalence, and we look at the homotopy class of the complex within that category. And Khovanov's proof directly go up to that setting and wrote them directly implicitly. And in that homotopy category, we do have an invariant. Okay, so it is an invariant. One can recover the Jones polynomial from there, and one of the interests is that it's a more powerful invariant. The second interest is a little hidden there, because one can try to, so Anna also talked about that, one can try to derive an invariant for links and also for maps between links. So if one takes a cobordism between two links, there is a way to associate to it a map between the associated complexes. So that detects things, some structures that's not visible from the Jones polynomial alone. So that's not exactly true here, because there is some functoriality issue. Which is very concrete. So writes down an example of a map between two links that can be presented by two isotopic succession of elementary cobordisms. And if you apply the construction of Khovanov to it, you get two maps that differ by a sign. So here it's only projectively functorial.
No, I never found that there is a sign difference. I just could not prove that there is.
So you give an example of a succession of moves that do have a difference of signs,
no.
Which doesn't.
No, I don't think so. I cannot prove that they don't have the same sign, but I never checked the sign.
I think it was Jakobsen.
Sorry, I cannot prove that they have the same sign, but I never checked the sign. I just said I don't know what the sign will be.
Okay, I'll read again your paper.
Okay.
So there is a succession of moves that give.
But it's not to me.
Okay. Sorry, my apologies. So anyway, there is a functionality issue, and this functionality issue was solved by Clark, Morrison, Walker, Capraro, and Christian. And so the version I'm going to talk about is the one by Christian, which consists in using these webs that Anna already defined. So we do everything alike, except that everything is oriented, and we allow for two labeled red-colored strands and faces in everything. And so here we just replace by the foam version of the differential. So if one does that, obviously the category is a little bigger, so we need more relations. And so they were all listed by Anna, and the only one that I really care about actually is that one. So what does this relation say? It says that whenever you have a dot that crosses a singular line, it picks up a minus sign. And that's all. All right, so in that version, I can just add, so back with some Walker, Caprow, and Blanchet. This becomes a functorial not invariant. Okay, so if one were interested in actually recovering a concrete homology, so a concrete vector space, one can just apply a representable functor on the Barnatan category that's given by a TQFT. So one can hit that with a TQFT that's described on generators, on generating morphisms. So a circle gets sent to Z of X mod X square as a Frobenius algebra, which means that saying that it's a Frobenius algebra tells us right away what I want to send each of the morphisms. And so, for example, I'll just write the product. What do I want to write? I'll write the coproduct, it's easier. So the split of a circle gets sent to something that sends 1 to 1 x, sorry, 1 to 1 tensor x plus x tensor 1, x to x tensor x. And one can list all of the definitions for this and check that endows z of x mod x square with the structure of Frobenius algebra. And one can play the same kind of game for the web version, and that's exactly that's all appears in Christian's paper. All right, I think I'm happy with it. So when we want to go to surfaces, the first observation is that all of this directly extends stupidly to surfaces. So I erase all of that. So if I take sigma, a compact, I'll take compact and orientable surface. So I'm allowing for boundary components. I'm fine with that. Then one can define a Barnatan category for sigma. We just take curves on sigma and cobordism between them in sigma cross I, and all the relations are local, so that's fine. And one can further define a knot invariant from there, because you just take a knot diagram on sigma, you locally replace all of the crossing with this same rule as before, and all of the proofs carry along because they are all local, so there really is nothing to do. You directly get a knot invariant in the homotopy category of this surface cobordism, and same for forms. So in the previous case, I can think I'm leading on an annulus, for example, and in that case, everything here lives on an annulus. And that's it. So, I guess I could stop now and say we're done. But it's not super interesting because that's something that doesn't tell much about what's happening. We want to compute a little bit more than that. So somehow in the Kaufman bracket story, defining the Kaufman bracket K module is not very hard, but what we've seen is that it's extremely hard to extract bases for these modules to understand exactly what how the algebra structure behave. And so this is the kind of questions we want to try to address also at the categorical level. And so part of the, so some of the hopes are that we can describe the structures at a higher level as well, which I think is an interesting question. But somehow the question that's driving us is more trying to go the opposite way and try to say new things about the Karpman bracket scale module by use of categorification. And one question that categorification should be extremely good at addressing is questions about positivity, because whenever we categorize something and get back to the original thing by taking, basically what we're doing is we are taking dimension, and the dimension of a space is always positive. So when you try to prove a positivity statement about some algebra, going to the categorical level is something that has good chances of proving what you want to prove. So the reason why we're doing all of this study with Paul is because we're trying to prove positivity statements for the Karpman bracket scale module. So if I have a few minutes, I'll say more about this at the very end. So I was trying to sell categorification not as a thing just for itself, but to actually do something with the Karpman bracket scale module. All right, so what goes wrong, and why am I not happy with that? So the first thing is that this is right. So this is not very meaningful. In the sense that once I've written that diagram, I cannot say much about it. So which I would like is something more computable. The basic recipe in the plain story was to hit the complex with the GQFT, a representable functor, and then be able to compute homology to compute dimension of spaces and so on. Great, so that's a good idea. But it turns out to be a hard one, and it's hard to find a TQFT here. The reason for it is that, and I explained that in the planar case, the TQFT is tautological. You just take the dimension. Well, you just take home spaces from the empty space to your curve, and that's all. And here there is more than the empty space for a general surface. You have curves on the surface that cannot be removed, and that yield basis for the Karpman bracket scale module. So one needs to think a little bit more about how to define the TQFT in that case, and there is not a canonical choice. And one of the reasons, one of the easy examples to see that it's a hard question is the following one. Say we consider this is green, okay? So say we consider this link on the torus, on the thickened torus. Then the associated Khovanov homology, Khovanov complex, looks like that. And we have two resolutions. One goes like that, the other one goes around the other way. So we have, in terms of...
In the back, maybe
it's not visible?
Here, okay, but in the back,
Okay. Do again in red. Okay, I describe things. So what I'm doing is I'm stacking a longitude over a meridian, and the result complex is made of two single curves, two simple curves. One of them has slope 1, 1, the other 1, 1 minus 1. So the point is that we have two simple curves that are related by a differential map that's locally a saddle. Great, let's hit that with, so here we have a cobordism of Euler characteristic equals to -1. And if you look closely at that cobordism, you will quickly find out that it's an unorientable one. Okay, so let's say we want to hit that with the TQFT, and because it comes from Khovanov homology, try to assign Zx mod x squared to both these things. Then, which I didn't say is that all of this is graded, and the degree is minus the Euler characteristic. And so when you look for a degree 1 map that goes from Zx mod x squared to Zx mod x squared, and you know that x has degree 2 in this construction, there is no solution. So this map cannot have any image in that story. So, well, that's okay. So no map on no endomorphism of the x mod x squared of degree 1. So as I adapted it against Heegaard, I said, well, that's okay, let's put that to 0. Let's assign 0 to it. And furthermore, Treyev and Turner later said, well, that's the only thing you can do.
No, but why do you assume that you have the x mod x square on the non-trivial curve?
Right, so one could look for other things. That's been explored partly by Treyev Turner, I think also by Kaiser. And my take on these papers was that that's the only thing you can do. So one could try other things, but so far I think nobody found any meaningful construction that really has something interesting to in that case.
But there is no abstraction that it should be two-dimensional.
No. No, and actually, so for trivial curves, probably you want to do the same thing as Khovanov homology. For this one, it's not clear, and actually in the Kaplan bracket scale module, what do I want to say? I want to say that in the scale module, this gets assigned to q plus q minus 1 or possibly minus. And yeah, when it's trivial. And a non-trivial one is actually a generator. Okay. So even sending it to a so somehow the choice of sending it to a two-dimensional thing is already something that can be discussed. It should correspond to a simple element of the category. And so here there already is something a little weird. But somehow still that seems to be the option that works best.
In some
well,
sense, it's forgetting the picture.
Yeah. Okay. Right, so the APS homology, maybe. So what they did is explicitly write images for all possible generating cobordisms and write down associated maps for them and check that yields a knot invariant. So for example, they assign Zx mod x squared for any circle, whether it's trivial or not. And then for generating cobordisms, so I'll do multiplication. There are several cases. If everything is trivial, then that's usual. So write it as well. 1 tensor 1 goes to 1, 1 tensor x goes to x, x tensor 1 goes to 1, x tensor x goes to x. Now if one of the circle is non-trivial, so if there is some topology going on over here, then they get something like 1 tensor 1 goes to 1, 1 tensor x goes to x, x tensor 1 goes to 0, which is different. Sorry, x tensor x. I said something stupid. X tensor x goes to 0 again. So there are slight changes in the definition, and then you can check explicitly at the end that these choices are all consistent and they yield a homological invariant, homological in that case. Okay. Oh, I forgot. I had one key thing I wanted to say to sell our work, and I forgot. So there is one issue in that theory, and I think that remark is explains the reason why going functorial is really important. So once one decides that this unorientable map goes to 0, obviously if I go, let me do it again. If I go from here to there, and back, I will get 0 because I just composed 2 0 maps. But so what happens here? Locally what we have is we have a resolution like that. We apply a saddle. We go to the other resolution. And then a saddle again. And so now what we see is that here in the middle, there is a cylinder. So that can be cut according to the neck-cutting relation, and that equals I'll be cheating a little. That equals this plus that equals this plus this. Now, you need to remember that this is a connected curve. So if I take dot here, I can slide it around and bring it over here. So these two maps are the same. And so this is 2 times, this is so 1 plus 1 time dotted identity. So what we're saying is because we've decided to kill to kill both of this of the terms in position, then 2 times the dotted identity, that has to be 0 by choice. So well, that's fine. That doesn't kill the whole theory. That's okay. But still, it means that we're losing a big part of the category of cobordism over the surface. And now, if we're going to the functorial world, the situation is a little different because here we have almost the same thing, but there is a 2-labeled wall in there that survives, say, here and here. And now when I do the same move of moving these dots around, I cross one wall once, and so I get a -1. And here I get 1 minus 1 times dotted identity, which indeed is 0 on the nose. So in the orientable, in the functorial version of this series, then we do not have to kill anything to define to define TQFT functors. So what I'm willing to sell is that if you just go functorial and do nothing different, then you have much more freedom in the construction and a richer version of it. So maybe one case that's quite interesting is the annular case, and so I suggest we do that in a little bit more details. And I think it will serve Paul's purpose afterwards. So in the annular case, well, so everything lives on an annulus, and so for example, we can go back to this example and try to say a little bit more about what happens here. And so if you've already seen Khovanov homology in some way, you probably know that these curves can be simplified in terms of smaller stuff, and in particular, each black circle can be simplified into two copies of nothing. So one can apply isomorphisms to that complex to make it, well, somehow to first expand it, but then allow for Gaussian eliminations and so homotopy equivalencies, and make the complex as small as possible. And so if I apply locally this process to this particular case, what I will get is something that looks like, so if I just expand everything first, then I get something that looks like two one-colored circles going to a direct sum of two copies of a two-colored circle. Same here, that means another one here. As a global shift as well. And here I have actually quantum 2 to the square, shifted by minus 2, whatever that means. So we get a simpler complex, but if you analyze the differentials, you also get some very simple things. And so what you get is a matrix of differentials where stuff look like this. One, maybe not, I won't do the other ones. So what does that mean? This is to be understood as, so what do I want to say? In the annular case, because we have, the annulus is S1 cross an interval, and so the curves I've reduced to are just parallel copies of the S1. Wrong. Parallel copies of, no, that's it, parallel copies of the S1. So there is a particular class of cobordism between these special curves that's given also by S1 equivalent cobordisms. And it turns out that one can reduce all the differential maps to the differential maps just to those particular S1 equivalent cobordisms if you allow for some dot placement. So what this means is that I have an annular cobordism that looks like this. And what I'm remembering here is just one section of that cobordism. And then I just take the S1. I pass from one to the next one by dividing or multiplying by S1. Okay. So, well, the first theorem I want to state is, let's write it here. Been used before. So, in this version, that's a theorem with David, but in the SL2 version, it's actually just a recast of results by Roberts and Grigsby and Wehrli. Say that so the category of foam or Van Hatten category over sigma over the annulus is equivalent to its full subcategory spanned by concentric circles. So what that means is that if you just restrict to objects that are trivial, in that, that are easy in that category, that don't have any trivalent vertices, any removable circle or anything, they actually basically they represent the whole category, because there is an equivalence between the whole category and the full subcategory spanned by these objects. But furthermore, in that case, morphisms are then spanned by S1 equivalent morphism. So what this means is that for any morphism between S1 equivalent objects, I can find an expansion in terms of S1 equivalent morphisms as well. Why are we happy about that? The reason why we like that description is that if you compute the Euler characteristic of such a thing, that's always 0. And if you now remember that the degree of, so here I allow for dots, and the degree of a dot is 2 times the number of dots. So what this is saying is that the degree of a dotted S1 equivalent morphism is always the number of dots, and that's always a non-negative integer. So we have a non-negative gradient. And so what this is saying is that this complex over here is filtered by degree, by a non-negative degree. And it turns out that the APS homology is the first page of the spectral sequence. Maybe it's second, and never know where to start. So because of this filtration, one can define an associated spectral sequence. And when you take the homology for the first time, what you find is the APS homology. And if you go to infinity, then you recover Khovanov homology. So that's already apparent in Robert's first paper, and it's been made clear by Grigsby, Licata and Wehrli. But there is a second comment I'd like to do. And so now if we look a little bit more about this description for the morphisms, and for example, we consider, so if I take that cross S1, so that's just a circle, and so here the annulus, that's the core of the annulus over here. So that is a cylinder. So I can apply the neck-cutting relation somewhere. Sorry, that's a torus. But I can apply the neck-cutting relation in some part by choosing some cylinder. this equals something that looks like this plus with a dot plus this with a dot elsewhere. And again, these two things are going to be the same. Both of them are a once-dotted sphere, and a once-dotted sphere is values 1, has value 1, so that has value 2. So in these pictures, if you have a circle, that's the same as 2 times the empty picture. And this is basically the defining rule of the Temple-Lib algebra at q equals 1, so in the non-quantum setting. And it's actually, so this observation generalizes, and you can prove that homes in this category are described by a dotted version of the Temple-Lib algebra. And if you take no dots, then you really get just TL2. But TL2, that's the endospace of tensor product of representation of USL2. So what this is saying is naturally what the category where you're living in is the category of representation of USL2. And so that indicates that the invariant that we have carries an SL2 action. And so that's a result of Grigsby, Licata and Wehrli that we've extended with David Rose. All right. So that gives a natural explanation for the appearance of this action. And so you only lose it when you turn on the extra differential, the higher degree differential, that does not commute with the SL2 action, and so Khovanov homology for the plane doesn't have this SL2 action anymore. So what do we learn here? The first thing is that it's a great idea to look for non-negative grading because it gives spectral sequences and it gives natural ways to define variants of homologies. And so what we wanted to do with Paul was trying to extend this characterization of annular homology to make that true for general surfaces, and try to get some extra grading from the topology of the surface that will be non-negative and allow for the same kind of definition for surface version of Khovanov homology. And the second thing we like about that is that this kind of structural theorem actually gives us more tools to study and understand Khovanov homology for surfaces. And so in that case, that connects to Anna's question before. When we assign Zx mod x squared to a non-trivial torus, so to a circle that's not removable, to an essential circle, this Zx mod x squared actually has a non-trivial SL2 action, and so it becomes a simple object in the category, and then that makes the decategorification process way easier. And now the decategorification of a non-trivial circle is that's a simple element, so that will be a generating vector in the decategorified basis, which wasn't true. Well, which is not true if you forget about this SL2 action. You do everything just in terms of vector spaces, and then you have to play around with coefficients to be able to extract from the APS construction the original Kaufman bracket scale module of the surface. Okay, I have something like 3 minutes. Is it so? So, well, I've stated the theorem. So I basically told you everything already. So the theorem, which is joined with Paul, is that, well, there exists, well, the foam category, or that, and is the same for that, over sigma, in case it's not the two-sphere, is non-negatively graded. How will you go about proving such a thing? It's actually a very simple proof. You first reduce to objects where you do not have any non-essential circles in them, and then you look at all surfaces of positive Euler characteristic, which would correspond to negative degree morphisms. Well, there are not that many. You can have 2 or 1. Euler characteristic 2 or 1. And you find a way to prove that these surfaces cannot embed in the thickened surface and between the desirable objects. So it's a very hands-on, and topologically it's not a very deep proof. But that does yield a non-negative grading on the foam category that's really determined by the topology of the surface. And so from there, you can define somehow the sigma version of Khovanov homology, which is which is obtained. Okay, if I denote K that's a complex together with the differential splits into its degree 0 part and its higher degree part, then one define K sigma to be the restriction to the degree 0 differential. And because of the non-negative grading, this is indeed the differential, which wouldn't be true for in general. So that is the definition, and then that's so up to functoriality issues. That's APS construction. So what I mean is that in spirit it's really the same thing, but for some reason we have to work in the functorial setting. In particular because you could say, okay, let's specialize that to the field z over 2z, and then the two should become equivalent because there are no sign issues anymore. But there are several places where we do want to invert 2 badly, and if we cannot specialize to z over 2z. So in spirit they are the same, but we are having a hard time saying exactly how they are. All right, and now one can use several representable functors to hit these homologies, and that yields. So if hit with representable functors with TQFT, then if we have an inclusion of surfaces, that induces a spectral sequence from K sigma to K sigma prime. So we can further play with the topology of the surfaces and do embeddings, and that yields there are associated algebraic operations on the side of Khovanov homology for surfaces. And again, those extremely depend on the fact that we did not kill dots before. We did not have to kill dots to apply representable functor. So here there are 2 things at play. The first thing is that one cannot have spectral sequences in the world of homotopy categories. There is no such thing as a homotopy spectral sequence, so we have to use a representable functor. And to do that, if we did not use functorial homologies, then we would have had to kill dots, and that would have killed all of the spectral sequences. All right, so in the last -1 minute, what's next to be done? There are two questions. The first one is I'd like to better understand what replaces the SL2 action in that case, and that's somewhat unclear. The second thing is we definitely want to use that to get to positivity statements, and that requires to categorize as well the algebra structure on the Kaufman bracket scale module, and that's somewhat hard to do. And so we are trying hard to achieve that, and hopefully we'll get to that soon. Thanks very much.
Thank you. Questions, comments? Can you say again the relation with the Kaufman scaling algebra?
Right. So.
In the general case.
So in here. Oh no, in here it's super easy. You have K, which lives in the category of complexes up to homotopy of sigma forms. And we restrict to degree 0. That's the definition of the environment. Just keep only the degree 0 part. Then K is the class of K in K0 of that. And that's the Kaufman bracket scale module. So the reason, what we've proven is that simple curves are simple objects in that category, and we are able to classify all simples in the category, and they match exactly the basis of the Kaufman bracket scale module. And they match the different bases. We have, we are able to realize one of the Chebyshev bases, the one that topologists don't like. And the other one, the one for the Chebyshev that we've seen so far, we know how to categorize it for the torus, but we don't know how to do that for a general surface. And we pretend that one does not need to do that to get positivity anyway.
So do you have explicit expression for torus for whatever common homology?
Yeah, then simples are, then it's just the same as at the decategorified level. You have simples that are classified by slopes. So you get parallel copies of curves. And the simples are Jones-Wenzel projectors put upon these parallel copies. So there is an algebraic description. If you're asking about specific computations, I think, yeah, no. No. We have a few basic examples, but not.
Okay.
If you want to complicate not, we haven't run any computation.
So it's in your paper.
One feature of the construction is that it's natural on the embeddings of surfaces. For example, if you have a knot diagram and a disk, you put that on a torus, embed the disk on a torus, and then run the usual computation, then you can see the same very defensiveness and have the vacuum.
But for purely torus knots, we haven't computed.
Well, the torus knot on a torus will be a simple object.
Yeah, for knots that are really not on the torus.
Question? All right, thank Hoel again. And next at 11:40.